Thanks, everyone. It's great to be here this morning. I'm Matt DeBergalis, one of the founders of the Meteor project. We're a team of about 30 people in San Francisco and around the world working on a full-stack JavaScript application platform, which means you can write a complete modern application for web and for mobile with a modern interactive interface in pure JavaScript. With Meteor, your code base covers all the parts of that app, so the parts that run inside the browser or the mobile device, perhaps on an IoT device or a thermostat, as well as the secure logic that runs in the cloud and connects to first-party and third-party microservices. Thousands of companies are using Meteor, startups building consumer and marketplace apps, SIs, ISVs, and enterprises too. So today I want to share the technical architecture behind Meteor, what we call connected client, and describe Galaxy, a cloud service that we just launched this week that runs Meteor applications inside of Amazon's new Elastic Container Service in the cloud. There are some unique DevOps challenges that come with running connected client applications. So I'll spend a lot of talk explaining what some of those are and how we've addressed those using the capabilities of ECS and the other parts of the Amazon stack. First, I'm not sure how much JavaScript background everyone has. I know Deepak mentioned Galaxy in his talk yesterday and made a comment about, JavaScript is that other world that is so far from back-end programming. So I just want to give a little bit of context here. We first announced the project in 2012. It's open source. It's, I believe, the most popular application platform on GitHub in terms of stars and activity. It's got hundreds of code contributors around the world and meetups in something north of 200 cities across the globe. We also have a network of over 100 training partners and development partners that build apps for clients including companies like Honeywell, Wrangler Jeans, the City of Hong Kong. And we're funded by Andreessen Horowitz, Matrix Partners, and others in San Francisco. As I mentioned, the most recent addition to our platform is Galaxy, which is the runtime that allows you to run a Meteor application. And the exciting thing about that for us is that it lets us offer for the first time a complete end-to-end experience in JavaScript. So whether it's the development or the deployment or the monitoring and operations of your app, there's a single group that you can work with to help you with all of the issues that come up during that process. Meteor itself you can think of a little bit like Java Spring or Ruby on Rails. The idea is to pull all of the technologies together that you need to be able to write an application. And make sure that all those parts are aligned so that you have a productive development experience. It turns out that JavaScript, unlike some of the other languages we've used in writing applications in the past, is very fragmented. So you don't have that consistent development experience across, for example, the way you'd use it in mobile versus the way you'd use it with Node.js in the cloud. And we've brought those things together. But it turns out architecturally, Meteor is quite different from a Spring or a Rails because in modern connected client applications, we have stateful connections between the client and the server. And that's going to drive a lot of important differences between the way that we run and operate these apps. So to give you a quick picture of Galaxy, this is our container environment built on top of ECS. It runs user applications inside containers in a multi-tenant environment that we operate, the Meteor company operates. Users get visibility into those individual containers, including real-time metrics of the CPU consumption, which we measure in ECU, Amazon's standard unit of CPU, memory, and other important statistics, as well as the number of clients connected to each particular container backend. It's designed to be a turnkey experience for teams that don't want to think too much about DevOps, but it's built on top of these open technologies so that teams with more sophisticated requirements or who want to have a more nuanced approach to their DevOps can have that option. With the help of ELB, we're able to schedule a proxy service that we wrote to route incoming requests from clients into the appropriate container. Do that in a way that guarantees high availability for applications that require it. And I'll get into how all of this works as we go through the talk today. But first, a little bit of context. So why all of this? Why is there such a different runtime environment for these apps? Why did we have to build Galaxy? Why WebSockets? It's really about a big change in the industry, a shift from websites that powered the last 15 years or so of the way we built applications. Websites built around the idea of links and forms, the idea of looking at one page at a time and then clicking or taking an action which would draw a new screen, apps that were viewed in a browser. A shift away from that to modern applications. with a much more engaging and interactive user interface and user experience. The big driver here, of course, is the rise of mobile, and the fact that now that we have a supercomputer in everyone's pocket, we can build a far more engaging, a richer experience than was ever possible when you built it around the idea of HTML and pages. So the leading edge of this transition were the consumer-facing companies, Facebook, Twitter, Google, and so on, who were able to create a different kind of user experience that drove key business metrics, like engagement on site or the ability to share things. But that now has carried across to everywhere, where companies insist on the same kind of experience for their customers because that's what their customers are used to. So we see the same desire for an interactive, engaging experience even in the enterprise or for a SaaS or a marketplace app. It turns out there's a big architectural difference behind that transition. The web was stateless. We all know this, right? It's built around this great idea that we can have lots of independent, horizontally scaled backends. There's no state between the client and the server, so therefore any client request can be handled by any server. This gives us a really straightforward path towards scaling and reliability. It's basically a request-response paradigm, and we're putting screens, HTML, on the wire. Very, very different now with apps. Apps are stateful, and I'll talk about why that is in a moment. We keep a WebSocket or some virtual equivalent of an open connection between the server and the client. There's a pub-sub model instead of a request-response model because the server is often initiating the push of data to the client. And it's data that we're putting on the network now, not screens. So the architecture is very different, and that shouldn't be a big surprise because we've done this before in the industry. In fact, we can look back 30, 40 years and see a progression of different technology eras in the computer industry, the way we built apps, and see these big shifts from one to the other. So for example, in the 70s and 80s, we wrote software on mainframes. The software ran on a big computer in the data center. We used a protocol like 3270 or VT100 to transfer screens to the user, which sat at a dumb terminal. And then with the rise of the cheap PC, right, the microprocessor essentially, we were able to move the applications to the desktop. And that gave us the rise of Win32, client server, transaction processing, all the technologies from the 80s and 90s that drove that era. We actually carried over very little of what we used in the mainframe era when we built these new apps. And then likewise, with the pervasiveness of the internet, maybe 15 years ago, very quickly we moved away from the client-server model to a model around delivering applications by giving someone a URL. And the advantages for distribution were so strong that we got the rise of Salesforce and Amazon and all of these websites that were built, again, using a completely different set of tools and technologies and languages from what we used to build Win32 client-server software. So it really shouldn't surprise us that when we move to this new era of connected clients, we should expect to see a similar degree of disruption and a similar set of transitions from the technologies we all knew and loved from the web era to technologies for connected client. And here's what drives that. So I mentioned stateful. There's actually a few reasons why these apps are stateful. One of them is because to build these slick, engaging interfaces, think about using Uber on your phone or Facebook or Twitter in the browser. You can't afford the cost of a round trip to the server every time the user interacts with your interface. In other words, when you swipe from one part of the app to another, or when you change the thing you're doing in the app, the data that you want to show the user has to already be in the device. And so inevitably, inside all of these apps, what we find is a cache, whether that's on your phone, inside the browser, on an IoT device. There's some cache of information that the server is maintaining so that the client can have a very rich, interactive experience without paying that round trip back to the server. And of course, once we have a cache, that implies that the server has to keep track of what's in that cache and is responsible for pushing new data to keep that cache fresh. So inherently, it's a stateful architecture, not a stateless architecture. Another example of state in this picture is that we now have code running on the clients. In fact, the majority of the code, if you count the lines, is probably running on the phone or inside the browser rather than in the cloud. So now we have questions of, how do I do a secure update of that code? How do I do continuous deploy when that really means pushing code updates down the wire into a running mobile device JavaScript container or into a browser? Here again, we need a stateful understanding of the exact set of clients that are connected to the app and an understanding of exactly which version of the software they're running so that the server can coordinate that upgrade across the wire. So that's the key difference here, is that we go from stateless to stateful. We're going to push data to clients in real time, and that code is going to run on both sides of the wire. This is very different from the architecture of the web. Here's another more nuanced way to look at the situation. If you look inside the way that the most agile companies are building rich interactive apps that run on multiple devices, you see a picture more like this, where there's a single app. It spans the network. So there are parts of it that run in the cloud and parts that run on the device, but it's a single application owned by one team. It talks to microservices, so whether those are internal services for authentication and billing or third-party services for geo or whatnot, those are maintained by separate teams, but the real win in development velocity is if you can have a single team that owns that app and doesn't have a federation between the group that's going to do the feature for iOS, maybe transferring their skills to the group that's going to do it for Android, and so on and so forth. And it turns out JavaScript is the ideal language for doing this because it's the one language that runs in all of the settings that application has to run. So if you want to build that yourself, you end up having to solve all these problems, right? You've got to have that layer that keeps the cache in sync, keeps your screen up to date, coordinates those hot code pushes across the wire. It's all the same in every app. And the concept here is to standardize and centralize those technologies that are the same across all the apps into a single open source platform, allowing teams to build the specific parts relevant to their app. So JavaScript's the only reasonable language for doing cross-platform app development. We've talked about why the architecture is different. Let's talk about the DevOps to support that architecture and how that's different. In fact, how that's a lot more complicated. And that brings us into Galaxy. So let's review what we want out of a cloud environment for a connected client application. We've talked about having persistent stateful connections, whether that's a WebSocket or whether that's a series of XHRs or other HTTP requests that mimic a stateful connection. We've talked about pushing code down to the client. We've talked a little bit about the idea that you really want to track those clients. You want to be able to count how many there are and understand the performance of each client as it's talking to the server. We've talked about all these microservices in the cloud that somehow have to get joined together in the application cloud code and then pushed into the client. And there's mobile considerations that we haven't gotten into around building new versions and pushing those into different containers for the JavaScript execution environment. So when we set out to build Galaxy, we wanted to address those problems. And as I said, we wanted a turnkey environment, so it also has to have the basics. Things like deploying your app with one command from the command line, scaling that app instantly from one container up to however many you might need. We wanted a scalable multi-tenant environment. And for us, scalability looks something like 1 million processes, 100 million active WebSocket connections to handle the growing number of applications running in the setting. I talked about the desire to serve the teams that don't have a sophisticated DevOps approach while also being suitable for teams that have more of an expertise and want to be able to integrate more closely with their environment. And one key element of that, I think, is the smooth path from going from a Meteor managed environment where you don't have to think about any of these questions, you push a button and your app's running in the cloud, to a customer managed environment where the application is running inside your own VPC. It's talking to databases, services, other parts of the Amazon stack or third-party software you're running in that environment, all coordinated by the same Galaxy technology. So we looked for a way to be able to carry that from the hands-off approach to the deeply embedded in your existing Amazon investment. And we wanted to make sure that the architecture was highly available, both in terms of consumer apps being highly available, but also the Galaxy infrastructure itself, the management layer and the other parts of the infrastructure that we build. So this is the architecture we landed on. Galaxy is a layer that sits on top of the infrastructure layer that we get from the Amazon environment. So the infrastructure layer is going to be responsible for the underlying compute and storage and so forth, as well as the container management layer, which we'll talk about. What we've built sits on top of that and handles the session management, the code deploys, the other things that are unique to the stateful connections between all these different clients that are connected into the system and the underlying common technology. So for us, containers was a no-brainer. I want to talk just about a couple of the high points here. First of all, when you have hundreds of thousands or millions of independent processes that all look basically the same because they're all running the same Node.js JavaScript runtime, containers make a lot of sense. They're obviously a lot more efficient than running a full operating system image for each of these. The spin-up time is essential, it turns out, in two respects. One is that we want to give a smooth, pleasant developer experience, and the ability to spin up an application or to scale that application in a matter of seconds instead of minutes turns out to be a really important part of creating that pleasant developer experience that drives adoption of the platform. It also lets us build around what I call a single-shot model. Essentially, because it's fast to spin up a container from a known fresh configuration, and you'll hear this story in Docker in general, that allows us to make some simplifying assumptions. And if things aren't as we want, if a container is misbehaving or if a virtual machine is misbehaving, the easy answer is simply to reset it, to delete it and allow the scheduler to bring up a fresh copy with a known good state. We also find layering really helpful, so the ability to have a consistent base image that's driven by our needs around the operating system, but then allow users to layer in other pieces of software that sit between their JavaScript application and the operating system. We see that as an ideal path forward to provide that in an open way. So that's the advantage of Docker and containerization. When you have a million processes, you need something more than just the containers. You need an orchestration layer. And there's a lot of really exciting options here. We look closely at not just Elastic Container Service, but we did a lot of work with Kubernetes and bringing Kubernetes to the AWS platform. I'm really excited about what Marathon is doing in the Meso space. These things are all changing very rapidly. For us, the decision to go with Elastic Container Service for our Galaxy launch this week really came down to the service argument and the tight connections between container management and the other parts of the infrastructure layer. So if you look back to that diagram I showed a second ago, I think of container orchestration as properly being one of the responsibilities of the infrastructure layer of your application. And the reason for that is that it's so closely connected with the other questions around compute and routing and networking that are in the system. So for example, the integration with ELB turns out to be a big time saver when using ECS. We can define a service. The service, for example, that runs our proxy system is automatically bound to an appropriate ELB endpoint. We don't have to build any of that plumbing to make that stuff work. Another integration example that's really valuable for us and unique to ECS is that a single ECS cluster spans multiple availability zones. So we can rely on the ECS scheduler and the task APIs and schedule tasks across multiple availability zones, both user processes and the processes inside Galaxy itself that need to run in a highly available way. That's a really valuable time saver compared to systems that are kept within one availability zone where we'd have to manage the failover or the transaction logic between the state of the multiple AZs. And we'll see how that works. The bottom line is it got us to market faster. The integration between the different parts of the stack all come together to allow us to focus on delivering a service to our customers. And that's the same argument we make about Galaxy, right? The idea of ECS being a service is very similar in my mind to the way we can talk about connected client management as a service we offer. And so it makes sense to me that the same advantages apply to us as they do to our customers. So let me talk a little bit about the implementation. This is the slide that Warren put in his keynote yesterday about Galaxy, and I want to talk a little bit about what we meant by this picture. So our architecture is split into a front end and a back end, a management layer that covers the user experience and the policy, and the back end, which is about the underlying scheduling of and execution of user applications inside containers. So the Galaxy UI on the left of this picture is about the list of applications that a user has pushed into the system, the desired configuration of those applications in terms of how many containers, what's the size of those containers, should it run in an HA configuration, what's the configuration information being injected into the application, questions like that. That's all managed by the Galaxy UI. And that information is stored in an application state database. In our case, it's a Mongo database, which holds, you can imagine, as a row per application with that desired configuration. The clusters, so each of these on the right is an independent ECS cluster, reads and writes from the same application state database. So it's a synchronized architecture, and I'll show you how that works in a moment, between the desired configuration and the actual execution environment to each ECS cluster. One of the reasons we're really excited about this direction is that the separation of concerns gives us some really clean stories around availability and reliability. The clusters can work independently even if they don't have consistent access to that app state database. And the other reason is that it gives us a path toward some future directions we want to go. So for example, while ECS supports multiple availability zones, it does run inside a single region. So the story for running applications in multiple regions is addressed by having an architecture that supports independent ECS clusters all synchronized against the same desired state configuration. Or I mentioned running applications inside user environments. So we can spin up an ECS cluster inside of a different VPC than our own VPC. That works fine. And that's a direction we're really excited to go in and think that the architecture of synchronizing this way gives us a clean path toward. So let's dive into one of those clusters. So I'm just going to look at one of the example clusters. And in these diagrams, I'll just show two AZs. We actually run in more, but just to keep the picture simple, we'll use two. So our starting point here is an application, in this example, running 4 containers in an HA configuration. Simple enough. This is the bread and butter of container scheduling in ECS. There's some more parts to it. We've written a custom proxy tier in Go. I'll show you how that works. Our proxy is itself run inside the same containers in the same clusters. And it's managed as an ECS service. It binds to the ELB, and so incoming connections from users run through the ELB into the proxy service that's appropriate, and then the proxy routes that WebSocket to an appropriate application container. We also wrote our own custom scheduler. So that runs inside a container, in this case exactly one container. We'll talk about why. And let's also add some other examples of applications or microservices that are running in the multi-tenant environment. Some perhaps in an HA configuration, some not. And finally, and I'm really fond of this architecture, the Galaxy UI, the application that you use to manage the Galaxy environment, is itself a Meteor app. And so we can run it inside its own container inside Galaxy. It turns out that that's a really nifty way of solving a bunch of the bootstrapping problems. It keeps us in a sane environment. And CloudFormation ends up being very helpful because it allows us to bootstrap this whole environment from scratch, including the Galaxy server that then manages the environment once it's up and running. So an administrator using the Galaxy interface is routed through the same exact ELB and proxy tiers into the same kind of container infrastructure as everybody else. They stand side by side. I want to dig into 3 particular areas of our architecture. The first one is scheduling. So I mentioned that we wrote a custom scheduler. Let's talk about why that is. So in a multi-tenant application environment, we have some particular needs that aren't addressed by the default scheduler. So I mentioned the first one. We want to be sure that for HA apps, the applications are scheduled across multiple AZs. That's available today. So that just got announced as part of ECS. We found it was actually very easy to do this with our own scheduler. But the idea, of course, is that I want to be sure, if a customer expects that we're not running on container instances that are all in one AZ. There's more to it, though. We also want to be sure that the individual instances are evenly loaded. So not only should an app be distributed fairly evenly across the container instances, but we want the reverse. We want to make sure that the instances themselves all have similar load. And the reason for that is that web applications are bursty. So what you want is a nice even distribution so that individual application processes can burst to the full core in the machine, far beyond the fair share that their container would give them. And that works best if you know that there's, roughly speaking, an even load across the different instances. We've also need a fairly nuanced way of thinking about application health, because we're not just interested in whether the Unix process inside the container is terminated or not. We're interested in, is it healthy? Is it answering requests? Is it answering those requests within a given latency or a given turnaround time? So the scheduler needs to have some visibility into that. And finally, we have an issue where, I'll go back to this picture. Certain tasks here, the proxy, the scheduler, are critical, the Galaxy UI. those have to be scheduled. So in a resource-constrained environment, if all of our customers scale at once and the instances don't scale up with them to match that rate, we need to be sure that we can still run the core processes that make Galaxy itself work. And the scheduler doesn't really have a story for how to do that. So we found that that's OK, because ECS's APIs are designed in a way that let us go into the lower level, the task management level of the API, and build our own default scheduler. And this actually worked very, very well for us. We've written our first version in production today is about 1,500 lines of Go. And it speaks to the low-level start and stop task APIs rather than the APIs around defining services. So we don't run user applications inside services. Instead, we run them as individual tasks, one or more, and we schedule them ourselves. And the scheduler includes a policy. So I've put part of that policy in here on the slide, and it mirrors what we talked about before. Schedule apps across AZs and instances, keep instances fairly evenly loaded, keep free space on each instance to be able to run the number of processes we know are needed by the Galaxy system. So it's sort of a blunt instrument for ensuring that we never starve our own system of the resources it needs to manage itself. And here's where we also implement rate limiting, for example. So because we're running untrusted user code, we don't really know whether that code is well behaved or not. A user might upload an application where the process spins or it doesn't behave the way you'd expect it to behave. So you don't necessarily just want to blindly restart a container if the process exits. You actually want to track how many times have we restarted this container, implement some sort of exponential backoff, and then eventually expose that problem to the user by way of the API. So we can look at that state sync diagram again, and what we see is it's the scheduler that's actually reading from the app state database. That's the piece that controls the individual application instances within the cluster. And one way to look at that is as a state synchronization process. So the scheduler task is reading the desired configuration from that application state database. Essentially, it's tuples of the application process, the version, we'll talk about versioning in a little bit, the containers, the number of containers I want to run, should they be in an HA configuration, what size containers should they be, and so on. It also calls list tasks and describe task from the ECS API. So that's how it gathers an understanding of the current state of the ECS cluster. And currently we do this by polling the ECS API for the state of the cluster every so often. It adds all that up and combines the policies we talk about to make a plan, an execution plan. And it writes that plan to the cluster by calling start task and stop task. It also writes back to the app state database. This is how we track the status, the health of each container, and when they exit, the exit code of the container so that we can push those into application logs and tell the user what's happened with their application. To ensure that the scheduler stays alive, we've created an ECS service that calls for exactly one scheduler task. So here's where the higher level ECS APIs work very well for us. The HA story here is, well, if the scheduler goes down, then we won't run that state sync engine, so we won't be able to scale containers up or down for a given application. Users can still ask for those changes, they just won't be executed on the back end. And if a container were to fail, we wouldn't immediately replace it, because that's the scheduler's job. But that's OK, because the service for the scheduler will reschedule a new task to run that scheduler process. And once it comes back up, it'll restart the synchronization process. And that's an idempotent process. So the state of the container will come back to the desired configuration over time. That's a reasonable failure mode, we think, for now. What we're considering doing is changing to a model where n schedulers run at a time. And we use Dynamo to broker a leadership election between them so that we can fail over more quickly. OK, so that's the scheduler. Let's talk about the proxy tier. So this is the part of the system that manages the stateful, persistent connection between the microservice backend and the client. And it implements what we call stable sessions and coordinated version updates. So these are the unique requirements around session management in a connected client application that don't really have the same analog in a web app. It's a share-nothing architecture, so we run multiple proxies. Any proxy can serve any request. It's a high availability architecture because you can run multiple proxies and multiple AZs. And here, too, we schedule it, as I said earlier, as an ECS service, automatically binding to the appropriate ELB. So let's look at a couple examples of how that works. Let's talk first about what we call stable sessions. So this is similar to what some people call sticky sessions in a web architecture. I'll show you the difference in a moment. The idea here is that once a client is connected to a backend, we need to keep that connection associated with the same backend throughout the duration of the client session. It's that specific backend process that understands the state of the client. It knows what's in the client's data cache. It knows the version of the client code so that it can issue a hot code update when the time is right. So the initial request from a client comes through the ELB, and we run the ELB in pass-through mode so that we can route WebSockets all the way through. The ELB randomly selects one of the proxies in the cluster. The proxy consults the app state database. This is our service discovery model to determine where the container for that application is running. And initially, it selects one currently at random. In the future, what we'll do is a least loaded model where it picks the container currently serving the least number of active clients. It opens a TCP socket to that particular container, and now we have the session established between the two. The proxy also cookies the session that came into that proxy so that future requests from the same client can identify which backend container was selected. So if the network connection drops and say the user's on a mobile device and they drive through a tunnel, this happens, that's OK. The WebSocket gets reestablished by the client. It carries with it this identification of which backend container it was previously talking to. That's an opaque identifier to the client, but the proxy understands what that means. And so the proxy reroutes that second connection, even if it's a different proxy that handles it, to the same application backend process. So we call this stable sessions because no matter how many interruptions there are in the connection, it will always try to route back to that proxy. Let's say that container fails, and this is a common occurrence in a container orchestration environment. Maybe its whole instance failed or just that particular container. Well, now we've lost the state. So we have to reestablish a connection to a new container. The proxy, when it sees that new socket come in, sees in the app state database that the container is no longer available. Or perhaps it's running but not marked as healthy. And so, at that point, the proxy makes the decision to reestablish a new stateful connection to a new backend. And it re-cookies the session so that future network interruptions will now route to the backend that's running on the right of the picture. So we call this stable because you want to route requests to the same backend as long as you can. This is different, for example, from a 12-factor architecture where you're trying to randomly route no matter when the request comes in. But once you have made the switch, you want to reestablish that new backend as the process that's going to handle future requests to minimize the number of interruptions to the user, the number of times that the screen has to flicker because data is reloaded into the cache or what have you. Let's look at another scenario. Coordinated version updates. So we talked about the clients having versions. Let's look at what that really means. So we have a user here on version 1 of the application, and the version is both on the client and the server. So I have a client v1 routed through ELB into a proxy, routed to a particular backend, just like we saw before. What we're going to need is coordinate the scheduler and the proxy to help make this work. So let's say we want to push out a new version of the application. The way this works is we're going to start by running new containers running a new version of the backend code or the service that's being upgraded. So far, this looks just like a normal update cycle. We wait for those containers to spin up and become healthy. So in this example, we've got 4 of the old and 4 of the new that are running, all managed as separate tasks spread across the container instance. Once we see the health checks pass on version 2 of the application, then we can start to tear down connections from the old one and move them over to the new one. So this is very different. If you caught the demo of ECS yesterday, one of the things we saw was of Empire, which is an open source stack for deploying 12-factor apps on ECS. One of the things we saw was during a version update, you could actually see the client flipping back and forth between the old container that was running and the new container that was running. And this was a hallmark of that stateless architecture. That's horrible in a connected client architecture because you're now running a new version of the client and you need that connection to run to the corresponding new version of the server. So when we tear down the connection, the client is going to reboot running the new version of its code. So we've pushed new code to the client over that WebSocket. And now the client, when it makes its new request, even though it's cookied for an old version of the container, the proxy is going to recognize that a version update is in process. So it looks instead at the version of the client, recognizes that the client's version mismatches that cookie, and picks now a new backend from the pool of healthy and available version 2 backends for that application. And at this point, we've established a stable session, and so future network interruptions will always be routed through any of the proxies back to that same v2 backend for that particular client. So this is called a coordinated version update. And that allows us to give users a smooth experience as we go from v1 of the app to v2 of the app. The logic for that is mixed between the proxy and the scheduler, which are the two pieces of custom code that we wrote on top of the generic ECS service. The last thing I wanted to talk about here was metrics. So application metrics and container metrics are an important part of understanding how your app is operating. A couple things to say here. So we collect metrics both at an instance level and a container level to display to the user. For the container level metrics, things like CPU utilization, network traffic, memory consumption, those are collected using the Docker Remote API. We run a collector process, one per virtual machine, which uses that API to aggregate all of that into one machine. That same process also pulls the proxies that are running on that instance. And the proxies have the list of which clients are connected to each container. So that gives us an active container count for the client. There's a single aggregator process, and these are both scheduled as services in ECS, by the way. The aggregator process rolls up all of the information coming out of the collector processes and pushes our metrics into DynamoDB. We store several different time series of data in Dynamo, so there's a cycle every 5 seconds of collecting performance information, and then we do an aggregate in the aggregator process and store time series on granularities of an hour or a day so that we can show longer ranges of time. Once that data is in Dynamo, the Galaxy UI can pull that database, and we've implemented a real-time Meteor database driver for Dynamo so that we can show users the state of their application in terms of the number of connected clients and the number of ECU units that the application has used. I mentioned ECU earlier. So Amazon uses ECU as a way to normalize processor performance across different generations of the actual underlying hardware. This turns out to be really important. The naive way to measure process performance in a container environment is the same statistics that Docker will collect, or you'll see if you run PS or top inside the container. And the problem is that it's reporting fraction of a core. So if you ask how much of my processor am I using, you'll get an answer that looks kind of funny because inside the container, your individual process is using what turns out to be a very small fraction of the core on the machine. What you actually want to show people is a sense of how much of the fair share of your container is being used. And what we found is that explaining that in terms of ECU rather than percentages is a good model for people because it helps them understand that you can burst above the guaranteed amount of ECU that we give you in your container. But what we really want to track and count is the actual number of ECU that your container uses. So at launch, for example, our containers are 1 gig of memory and half of an ECU. But they're running on larger instances, so they can burst into 2, 3, 4 ECU at a time up to the maximum amount that one core on the machine can deliver. And again, that's why we want to be sure to separate the different applications evenly across instances so that there's the most opportunity to burst onto those full cores. So as I said, we just launched this week. Our experience so far in ECS has been really good. And there's two things in particular I think have worked well for us. One of them is the loosely coupled architecture around synchronizing state between the app state database and the scheduler. That's allowed the front-end team on Galaxy to be able to build a normal management app in Meteor without having to dive into the details of the Galaxy ECS integration or the infrastructure as a service configuration. The back-end team can start from that app state database and focus on the interchange of data between ECS and our own application state. So that's allowed us to move much, much faster with the what turns out the bulk of the code in Galaxy, which is the management layer and the policy. The other thing that's worked very well for us is high availability. We've had some experience with this over the past few weeks. So a number of the services we use had outages, I guess it was about 2 weeks ago now, that were widely covered. All of our applications for our customers stayed up throughout that outage. So the ECS infrastructure did what it was supposed to do. There were outages in terms of being able to call ECS APIs. So there were windows of time when we weren't able to scale applications up or down or restart processes that had failed. But the applications themselves stayed up. The Proxy Tier and the ELB that routed into that all worked well, and users didn't see downtime. So we're really delighted with the HA architecture that we've settled on and the ability to do that even in a large distributed system where things do fail. Some directions we want to go here that we're excited about. I've mentioned the idea of running multiple clusters, and the real drivers here are customers who are asking to run their applications in other regions. European customers, for example, aren't super excited about US East in many cases, as well as on-prem. So we see run in your VPC as the new on-prem model, and we're very excited to be able to take essentially 100% of what we've built in our multi-tenant setting and bring that over to an individual customer inside their own Amazon environment. There's another interesting area of work around cost optimizations. This came up in the keynote yesterday, and I was really happy to hear that. So we're really excited about the opportunity to use different kinds of instances. For example, you could imagine running some of these container instances as spot instances. And you can run the scheduler works in spot instances, and then you can start to run tasks on these instances. Because we have embraced the idea of containerization, and because processes are, in some sense, expected not to last forever, it opens up a lot of doors, we think, in terms of distributing application load into the most cost-effective places we can, serving the needs of our customers, or trading off between different levels of instance reliability or instance capacity. So again, we launched this week the obligatory "we're hiring." We're really excited to add people to the team working on ECS and building against this stuff. I think it's fair to say Amazon's excited about what we're doing, and I'm very happy to take your questions. Thank you.